All right.
Giovanni is still.
Oh, Giovanni is here. Where's Giovanni? All the way in the corner. All right. The first speaker is Brian Page. He'll talk about jets and EA as a probe of hadronization and energy loss in the cold nuclear medium. So today, as you realize, we're having two talks about jets in cold nuclear medium. So this is the first of the duplex.
Okay, well, I'll actually be talking about very little of this, mostly talking about jets and working towards using substructure as a probe of EA. But a lot of the nuclear stuff we just haven't gotten to yet. So it's more about understanding the substructure variables at an EIC. So a lot of what I'll be showing, well, what I'll be showing is exclusively EP simulation, but hopefully hopefully making connections to the EA stuff that we just haven't gotten to yet. Also, I don't have anywhere near an hour's worth of material, so feel free to ask plenty of questions. So a quick outline of my talk. I'll just briefly go over some general jet properties that we can expect to see at an EIC. I want to talk a little bit about underlying event, and then I'll get into substructure. So talking about mainly angularities. So I'll do some theory simulation comparisons, talk a little bit about ways to look at power and higher order corrections, and then end with Quark Gluon discrimination. So just really quickly, the relevant subprocesses that we have simulated, looking at resolved, QCD Compton, photon gluon fusion, not so much the leading order DIS process, but it's simulated. Some details about the simulation. So again, we're doing what I'll show today is electron-proton events generated at the maximum energy. So this would be 20 on 250 electron on proton. Of course, with heavy ions, we can't get up to 250. I'll make some comments about that. Cut on inelasticity, we'll be using for jet finding the anti-KT algorithm with a couple different radii that we'll be comparing. Jet finding is done either in the bright or the lab frame, depending on Q-square range we're looking at. And basically we build up the jets from all stable particles with PTs greater than 250 MeV in the nominal acceptance of an expected EIC detector. So the first thing I want to talk about is maybe the most basic quantity for a jet. It's transverse momentum, and kind of make the point of, point out that these are going to be soft spectra. So the maximum energy we can expect at an EIC is about 141 GeV center of mass. And we can see here that these are very soft spectra. They start to peter out. This is the jet PT. They start to peter out, around 30, 35 GeV. We can't expect PTs much greater than that. And we're not talking about a huge number of jets to see. So these are spectra for two different energies. These are kind of nominal EP energies at Q squareds of 10 to 100, or 1 to 10, and 10 to 100 from the photon gluon fusion process, normalized to, this is counts per inverse femtobar. So kind of, in principle, I can take a jet finder and I can cluster whatever I want and call it a jet, but at some point that stops to be stops being a useful object. So how low in PT can we go before that jet stops kind of representing the parton, or where does the theory start to break down? So it benefits us to press as low in PT as possible, because that is where the events are. If we have to start talking about jets above 10 or 15 GeV, then we're starting to talk more about rare probes. And so here I show again, so this would be representative EA energies, either 90 GeV, so that'd be 20 on 100 GeV, or something like root S of 40, 10 on 40 GeV. And you can see here, it just, as you go down in root S, the problem just gets worse. The spectra gets softer, the kinematic reach gets shorter. So really being able to get down to low jet PTs would help. So here you see the same kind of story. This is just now the Dijet mass spectrum instead of the inclusive PT spectrum. Again, this is for photon gluon fusion events. And again, it's the same story for 2 different Q-square ranges, and then 4 different energies, EP energies and EA energies on the bottom here. Another issue, especially with substructure, that we'll have to contend with is the particle content within the jet. So this is the number of all stable particles within a jet as a function of the jet PT for 2 different Q-square ranges, and kind of the 2 limiting cases, 2 limiting energy cases. And you can see, so if we have a cutoff of about 5 GeV, we're talking about, at the lowest, on average 5 to 6 particles, and then as you get higher and higher, maybe up to 10. And this, remember, is all stable particles. So every pi0 that is in my jet will give 2 photons in this. If I just look at charged particles, this average drops by about 1.5 to 2 units. Pretty flat across PT.
On the low energy end along the jet.
I mean, so again, when I ran my jet finder, I just put in like a threshold of 1 GeV. So you should really, I just didn't cut off the plot. So anything below 5, I don't really, 4.5 or 5. I don't know
what the low cutoff was.
Yeah, it was 1 GeV to run the jet finder. And the particle PT cutoff was 250. So in the context of substructure, I'll talk a little about jet radius later. I just wanted to bring this up when considering jets as a surrogate for the parton. We really want to basically, we see that the larger our jet radius, the more faithfully the jet represents the parton. So kind of what I've done here is this is the Dijet mass versus the mass from the generated mass from PYTHIA, and for 3 different radii, 1, 0.7, and 0.4. And you can kind of see this is for the photon gluon fusion process. And as we have a larger radius, we kind of more faithfully reproduce that generated mass. As we fall off, we start to underestimate the partonic quantities. And you also see this little tail here. This is kind of from mismatched Dijet. So this is basically if I have 3 jets or something in my event, and I just pick I pick one that didn't represent the partonic hard scattering, and then you get this little tail. But for reproducing the partonic kinematics, we're really favoring a larger radius to do that. So I briefly wanted to talk about underlying event. So one of the trade-offs, especially in AA collisions or even like high luminosity PP collisions, between when you go to higher and higher radii, you get in more underlying event kind of junk that contaminates your jets. And we wanted to try to quantify that a little bit in EP. So this is a typical EP Dijet event. You can see it's relatively clean. We systematically studied this in PYTHIA using this kind of, we call it like a regions method. I think CDF, or I think CDF pioneered this. So basically we have a trigger jet, and then we define an azimuthal, 4 azimuthal regions around that trigger jet. So we have a toward region, an away region, which would pick up the away side jet, and then 2 transverse regions, which would be sensitive to our underlying event contribution. And so you can see here the average number of charged particles and the average summed PT of the charged particles as a function of this, oh, that got messed up, this delta phi runs along here. So this is your toward region, this is your trigger jet, and then you can kind of see the underlying event activity in this region before we start to pick up the wayside jet, and the same for the PT contribution. So we can see the underlying event activity is relatively small here. We've also compared that with PP collisions from STAR at 200 GeV and find that they're relatively comparable. I think it'd be interesting to do a similar kind of study using PA data from STAR as well, to hopefully make a connection to the EA collisions. All right, so on to the kind of second major part of my talk. This is looking at jet substructure, specifically the angularity. So again, one of the things we want to try to do with jets at an EIC is to explore the properties of cold nuclear matter. And the idea is to look at how a parton moving through that matter radiates its energy. And by looking, so the substructure variable is sensitive to how that energy is distributed. So the idea is that by looking at these various substructures, observables in EA and EP, we can get a handle on some of the properties of the cold nuclear matter. And so what I'll be talking mainly about is what we call angularity. It is just the sum overall of the PTs, the transverse momenta of the particles inside the jet, weighted by the distance of that particle from the jet thrust axis to some power 2 minus A, where A is a continuous variable that you can change, and then normalized by the jet PT.
A is 1. Is that just the jet shape?
Yes, so A of 1 I think is called like jet broadening. A of 0 is jet mass. Both A of 2. I think A of 2 actually. Well, I don't think you can do. I don't think you can renormalize A of 2. Yeah, I don't think you do A of 2.
I thought that's good.
So yeah, so everything I'll show is for A of less than 1. I think you can, so everything we have now you can do, so the theory setup, so we've been working with Felix and Kyle Lee, and I guess the setup they have can handle everything up to an A of 1, and then they have to like change out some numerics to go above A of 1, so I won't show anything there. But I think, yeah, things break down when you get up to 2. Yes. So I'm going to change around my cuts and my region a little bit. So I'll just mention now we're going to be working in the photo production regime because that's just, I guess there were some numeric considerations that, you know, they could do these calculations easier. So that's just where we've started. So yeah, now we've moved to the photo production region. So we're looking at Q-squareds between 10 to the minus 5 to 1. Again, we'll be looking at resolved. So that is the, so the resolved and the direct. So photon gluon fusion, QCD Compton. So here I'm showing a jet radius of 0.8. I've tightened my inelasticity cut a little bit. So now I'm also working in the lab frame. So everything here is shown for the lab frame. And so here we see 2 cross-section comparisons, theory to PYTHIA. So again, anti-KT, R of 0.8, root S of 141. So this is for jet PTs greater than 4, and this is for jet PTs greater than 10. Although it's not, there it is. Jet PTs greater than 10. Again, for the resolved and the direct processes separated out. And here you can see some theoretical uncertainty bands compared with the PYTHIA results based on variations in the relevant scales. So you can see PYTHIA does a relatively good job of getting the cross-section, which is good. We don't want to be simulating garbage. Yeah, so that's setting the stage now for the angularity comparisons. So here we see for 5 different values of A of positive 0.5, 0, minus 0.5, minus 1, and minus 2. So the 2 colors are 2 different radii. We have R of 0.4 in yellow, R of 0.8 in red, and then the corresponding PYTHIA curves in this kind of purplish and then
What do
blue.
you mean theory versus PYTHIA? I don't quite understand what you mean by that. I mean,
So-
PYTHIA is not experiment, so it's theory.
It's not theory either.
it's not theory. It's the simulation that we're using to generate the event.
So what's missing in that?
So I mean, yeah, I mean, it's like the detailed comparison between what goes into theory and what goes into PYTHIA.
So when you say theory, what do you mean?
So this is so what is this? This is I guess a fixed order.
So I think it's
NLO,
the next leading order,
yeah,
the
it's-
cross-section with the next to leading log summation of the output, which is none of which is in PYTHIA is leading log all the way.
So this is basically next to leading order comparison against the leading,
Yes.
basically.
Well, okay, there's a catch in that because in the Monte Carlo shower definitely has some leading log summation in it, but they're doing next to leading log summation on the output.
Insofar as there's a large deviation between PYTHIA and theory, that makes you worried that the theory maybe needs even higher order corrections.
I think their statement is that PYTHIA needs improvement.
Well, it seems like both would have, if you did a right to leading order and you're doing a right to next to leading order and there's a big discrepancy, it seems like next to leading is support.
We'll have to start calculating.
Maybe, I don't know.
I mean,
What do I know? I don't know.
Maybe not for negative E, just go to negative E, so we seem to agree, right?
Yeah, so, you know, of course, things agree within the scale uncertainty. But yeah, you see, so the dotted lines here are the kind of the prediction at the natural scale. And yeah, there is a shift and definite shape difference.
Sorry to interrupt again. I think we want to also point out that if there is an underlying event, there is initial state radio, there is multi-particle interaction.
Yeah, so none of this is
are in
groomed.
theory.
Yeah, there's no grooming here. Yeah, this is.
And what do you mean by natural scale charts? What's natural?
You'd have to ask
So does that
Felix
mean
what the
if-
natural scale is.
so does that mean
It's
if
what
you-
they ran the.
Does that mean if you improve your calculation, the theory calculation, by taking into account underlying events and fragmentation kind of effects, that you get closer to PYTHIA?
Well, so I wanted to bring up this as well. So if you went to see Felix's talk from week 3, he had this slide where he showed, so this is a comparison with data. This is jet mass now data from the LHC at 7 TeV. And so you see the bare next to leading log calculation here in yellow, and it badly misses the ungroomed jet data. But then they parameterize some non-perturbative effects using this shape function f. And with one parameter, they could then pull their perturbative calculation into agreement with the data. So I think what I would say here is that you know, we could play a similar game here. Definitely need less of a, you know, so there's some parameter here is set to 8. I don't know exactly what the parameter means. It's somehow quantifying the size of these non-perturbative effects.
So does this mean that basically this jet tau is not a perturbatively calculable quantity? So if you need some non-perturbative extra input with Atlas data, or is there some prospect that somehow some improvements in theory will
So this is I asked Felix this question in our probes, and he said he's arguing for grooming. Right? He's saying if you groom the jet, then the PYTHIA calculation and the NNL calculation would match up, right?
That's the claim. I haven't seen the plot. But
okay, so in some sense, the tau that is compared to here isn't the good perturbatively calculable quantity. You want to groom the jet, so you want to do something different to the jet on the experimental analysis before you get something that you can
calculate the tau.
Then calculate the tau.
Yes, that's right.
But are you sure it's really perturbatively calculable then? I mean, you know, there's a real question. Are you calculating something which is perturbatively calculable?
But then there is a plot actually that in that case the next leading order is very close to the, so then it's perturbative.
Yeah, but I mean, it's sort of a theoretical question, isn't it, which you can kind of know without having to do comparisons to data. And it's something
but this is a
perturbative you should know.
No, but that's what you're saying, right? Leading order and next leading order.
Things like thrust, I mean, sorry, I really haven't thought about it, but things like thrust were invented to stay away from perturbative effects, right? They were being perturbable, I presume. This quantity here, I already forgot its name.
Angularity.
Angularity, sorry.
Well, okay, so this is mass. So mass feels a lot of the soft stuff that you soak up.
So it's not insensitive to.
I guess
non-perturbative.
that's what Felix says.
But then, I mean, look at this function. I don't know what k is, this fi of k, right? If k is identified with mj or mj squared or something, then yeah, sure, it will have exactly the shape of the data, give or take, maybe. right? It's an exponential fallout with some sort of, okay, it has a linear rise. T is mj squared, then it will be a parabola on it. Well, it's small mj, fallout. And you don't need to do any perturbative calculations. Anyway, I don't know.
So I just want to mention a couple other things. Yeah, so here you see, so this is the relationship between angularity and jet mass. So if you take A as 0, that should be equal to the mass squared over PT squared, PT of the jet squared, plus higher order. And so one thing the first thing actually that I did with this was to calculate tau 0 and compare to the mass. And what I found was actually one of the things, so if you want to relate angularity and mass at an EIC, one of the things you'll have to be careful about is because we're at low PTs, the masses of your actual particles matter. So when I made this comparison at first, so basically I calculated my angularity and then I calculated my mass by just summing up the 4 vectors that went in of all the particles that went into my jet, and I got this red curve, and I thought I was stupid and doing something weird. But what it actually was is, you know, if there is a neutron floating around in your jet, the mass of the neutron actually matters. So if I just took all the 4 vectors and set them to be massless, I recovered pretty well the relationship. So if we're doing this kind of matching at an EIC at low jet PTs, it's just something to be cognizant of. Another thing, being more of an experimentalist, I should say something about the detector. So of course, this is all being done at particle level. So I know exactly what's going into my jet from PYTHIA. I know the exact 4 vectors. But of course, that's not what we detect. So for example, if we don't find the neutrons or the K longs, either because we don't have a hadronic calorimeter in certain regions, or just the pointing resolution is bad enough, we move from this blue curve to this red guy. And then if we also exclude the photons, so basically if our EM cal doesn't have decent pointing resolution, then we get this green guy. So of course you can think about unfolding these, but this is more just an argument of we'll need good good spatial resolution to actually to minimize the detector effects on this observable. So I want to talk briefly about now a method for trying to get a handle on higher order correction terms. So this is the formula I've been using. You can also write the angularity, and I guess for historical reasons it's called E plus E minus angularities, where now you, again, you sum over the PTs of the particles with the exponential of now the eta of the particle times 1 minus A. But for this formula, the particle PT and the particle rapidity are defined with respect to the jet thrust axis. So instead of the event axis, we transform into the, so now that our jet thrust is the z-axis, and then we can define, then we measure PT and eta, and normalized by the energy of the jet. And you can actually relate this guy and this guy via this relationship here. So you just have some prefactor multiplying your tau E plus E minus, and that gives you tau A, and some of these higher order terms. So if we take a ratio, we can calculate both these guys, and of course this guy. And so if we just take a ratio, we can start to get sensitivity to we can explore how sensitive we are to these higher order terms.
This is strange. So it's higher order in what? What is being expanded in? I'm a bit confused. So they saw this in the previous.
In tau.
So you assume it's always small, right? Is it? I mean, just looking at the definition, maybe for non-experts, is not.
Yeah. So I think there's.
So basically,
Well, there's some relationship between radius and tau that allowed you to factorize things. I think tau has to be smaller than your radius in some sense.
Much smaller.
Much smaller.
yeah. So I mean, I was just thinking that basically both these taus are something proportional to the radius to some power. Right? Yeah, both of them have a 1 over PT of the jet, so 1 over a large scale, and then on the rest, that's the numerator is small. I assume one should. So one all the time is thinking of tau as being small.
So it's essentially twisted function.
That'll be something.
What is the expansion from it?
Yeah.
It's almost the same as 1 over PT to some power.
Yeah, so if one looks at 1 over, so the first tau, there the 1 over PT is the PT of the jet, which is big, and then the delta R to some power, which well, at least for, yeah, so A not being too large, the delta, you're having delta R, and delta R is like the angle of the particles with respect to the jet axis, so that's a small number.
So
If we're talking about the jet, then all these delta R's
in the framework here, these are the relevant scales for the formalism.
So somehow the whole assumption all the time is that tau is parametrically small.
Yeah. And much smaller than R. So plus.
No, delta R is R. Delta R is R, more or less.
Right, but R is much larger than tau A for this scale hierarchy. Or it is some power. Tau is much smaller.
All right, so yeah, if I form this ratio, I can just plot it for various, so for two R values, this column is R of 0.4, R of 0.8, jet PT is above 5, jet PT is above 10, and then just kind of three representative values of A, -2, 0, and 1. And so the larger these values and the more offset from 1, the more influence from the higher order terms we get. So we see for any given radius in PT, the lower we go in A, the more contribution we have. And as we go up, that contribution decreases. We can look at now just the PT dependence as well for just the two limiting cases of A now, -2 and 1. And these these curves have been scaled to have the same normalization, so you can just see a little better. And so you can see the PT has little effect except kind of in this extreme region of large R and very negative A. And here even the difference isn't too great. The radius comparison is more pronounced. Again, this was A-2, so this is kind of the most pronounced influence from the corrections. And so now you see the two curves are for the different radii, 0.8 and 0.4. So you see moving to smaller radii helps reduce these corrections for both PTs here. And at an A of 1, where these terms were suppressed, changing radii has minimal effect. And so that's basically what I just said. So like I said, to start off, we haven't actually simulated the propagation through nuclear matter or done the jet finding there. We just haven't had time to do it, but as a way to maybe see if this is sensitive at all to different radiation patterns, I looked at Quark Gluon discrimination. The idea being that gluon jets should be somehow fatter, the energy more widely distributed. So to see if these angularity variables were sensitive at all to that, if we could discriminate between quark and gluon jets. And so that's what we see here for two different radii and two different PT. Now the curves are for light quarks are blue, gluons are red, and then I separated out heavy quarks as well. And you do see, some separation. It's not huge, but there is some there. This is for an A of 1, an A of -2. Now plotted, this is the log of the angularity, so you can see a little better the same kind of story. Of course, we have to be careful because there's probably a selection bias in here. So for R's of 0.4, we don't see as good separation. But again, if we require our jet to have a smaller radius, then we're probably selecting those gluons that fragmented to be more collimated and thus look more like quark jets. And so we're just not, we're kind of biasing ourselves to pick the gluon jets that match the quark jets. But it also points to, maybe we, when we're doing these kind of things, we want to use a bit larger of a radius, so we're not biasing ourselves. That brings me to my conclusions. I went over some general jet properties, mainly questions about the PT. We compared the angularity in Monte Carlo and theory. We presented a method for looking at higher order corrections, and we showed that this variable is somewhat sensitive to the energy distribution in the jet due to quark versus gluon fragmentation. So the next steps, obviously, we have to do this all again at expected EA energies. We actually want to, run this through some model of the cold nuclear matter. We can look at things like grooming. We can also look at things like different recombination schemes, which aren't sensitive to the soft recoils. And doing some comparisons with star data might be interesting as well for quantifying things like underlying event and such. So that's what I got.
All right. Any questions, comments, concerns? Yes, Daniel.
So I was wondering about this angularity observable. So people proposed it to look at for medium effects because it was sensitive to this difference between quarks, light quarks, heavy quarks, etc. Is that the reason?
So we wanted to, so yeah, we were kind of thinking this might be a way to use jets to look at these questions. And so I think,
this angularity observable.
so like, so Felix and Kyle, I think were interested in looking at it for different reasons, just more general theory reasons. And so we,
If you don't know those reasons, or I didn't hear the talk by Felix, so I don't the puzzles why someone would look at this particular observable as a function of this A.
yeah, I think you know, they want to do these calculations as well for the LHC. I think I'm not 100% sure of their exact motivations, but this is something that they've been interested in looking at, and so we figured this is a good place to collaborate and see, you know, to understand these and then see if they can actually be useful in these probes of matter.
Because you said it's on your slide it shows sensitivity, but you just said shows somewhat.
Yeah, so I mean, it's definitely in, you know, it's definitely a question, you know, so if we, you know, we simulate like a brick of cold nuclear matter and then we change, you know, some, you know, we turn a knob a bit, change some parameter, how much is our angularity going to change? That's what we have to do to get.
But because you said it shows that it is somewhat sensitive, you already expect it doesn't.
I mean, I wouldn't read into the sum. I'd put a more positive spin on it and say if they didn't show anything, if it was just dead on the same, then we could probably say, you know, what's the point of moving forward?
So can I ask maybe a question related to what Larry was asking? So it seems like there is a discrepancy between PYTHIA and theory, and that's without nuclear effects, right? This is just for protons. So how? So I mean, is the situation possible that, you know, we do EA, we get some sort of nuclear modification, but we can't really pinpoint it because of, and maybe it's a very naive question, can we pinpoint it if we have, even for EP, we have such a discrepancy in theory predictions and the data disagree with either curve you showed, either the PYTHIA or the theory prediction. And can we?
I mean, I'd say the agreement's pretty good. we were surprised, you know. You know, we just kind of like threw these together. We didn't really do much, and you know, the curves are within the scale variation. It's
Can I comment on this? I mean, it showed a little early as well when you asked this question. So all of this started around 2014 when there was this observation that we need to do the summation to get narrower jets, right? So the usual way is you just do fixed order calculation.
In the medium.
No,
Or
in vacuum. Forget medium.
but they always have the summation of CCFM type summation. I'm talking about multiple emissions.
Yes. So if you calculate the jet cross section, you would calculate a fixed order, right, with a certain angle or whatever. But then you realize that if you make the angle much smaller than 1, then you have to do some kind of summation to get from R of 1 down to R of something, right? So there was this whole formalism that started like 2014, 2015 by Gupta and Salam and all these guys. And this is an extension of that line, right? That can you take this UV sum formalism and apply it to things like angularity, things like that. And there is a little tension between, because even after you do this to summation, there's still a non-perturbative effect. And when you get down to narrow jets, non-perturbative effects are not as small anymore. Okay, so if you look at these papers, right, there's a leading log summation, and the next leading log summation, and then there is a non-perturbative effect put in. And there's still a lot of discussion in the community as to how much that non-perturbative effect is versus how much the effect of next reading of law of summation is. So I would say this is a little bit of an open thing.
So that means it's an opportunity.
It's an opportunity, of course. I have a student working on this, right? This topic right now.
All right, any other questions, comments? If not, let's thank Brian again. Okay, so organizers have a question to the crowd. Do we want to break for like 15 minutes, grab a coffee, or roll out some cookies?